everyone, and welcome to TLE Eliminators video solutions to the CP-31 sheet, where we'll be solving the problem 7 out of the 1600 written sheet. The problem hits different. So let's quickly go to the sheet and let's open up the problem. And yeah, let's quickly go through the problem and then we'll discuss the solution to it. Okay. So in a carnival game, there is a huge pyramid of cans with 23 rows. Okay, 23 rows numbered in a rectangular pattern as shown. So it's like a pyramid, like 1 and then 2, 3, then 4, 5, 6, 7, 8, 9, 10, so on. You can throw a ball at the pyramid and it hits a single can with the number n squared, right? So each of the cans are labeled with n squared. This causes all cans that are stocked on top of the can to fall. That is, the can n square fall, the cans directly above n square fall, and the cans directly above them fall, and so on. For example, the picture shows that the cans which would hit if 9 square fell. Okay, so if 9 square would have fallen, that means 5 square fell and 6 square fell. If 5 square fell, that means 2 square fell and 3 square fell, and so on, right? What is the sum of the numbers on all cans that can fall? Recall that n square is n times n, and there are 1000 test cases. N goes up to 10 power 6, and there's no limit over n for all test cases. Okay, so pay attention, there's no limit of n over all test cases. So it's possible that each test case has n equals 10 power 6. Okay. For each test case, output a single integer, the sum of numbers on cans which can fall. And we have to keep in mind that long should be used. And some test cases are given. For example, check the test case 2. So if can 2 square is hit, if the can 2 square is hit, then this can is going to fall as well as the 1 square can. So 1 square plus 2 square equals 5. So that's why the output is 5. So that's how this question works. Okay. So now before getting into the question, let's think about what is the expected time complexity, right? Expected time complexity. And so now from the structure of the question, we see that there is no constraint on the sum of n, right? So basically we need some kind of solution which is big O of n. And like, so the number of test cases will get counted, right? Because the number of test cases is not independent of n right now. So at most, like big O of n plus number of test cases for each of these 1000 test cases may be about root n or big O of n plus t log n, right? Roughly this much big O of n plus t square. Roughly these kinds of something like this time complexity will be there, right? N log n plus t log n, something like this. These are the possible time complexities which would pass for the given question. So for each test case, we have to do some limited amount of work, as well as we can do some amount of pre-processing on n. So this is the intuition we get, right? Some big O of n-ish pre-processing, right? This is the intuition we're getting, pre-processing. Then each test case should be answered in something like big O of constant, big O of log n, or big O of root n, or something like that, or similar. Okay. So how do we do this? There are multiple ways to approach this problem, because of course it's just a pattern matching kind of problem. So there can be many ways to approach this. However, so let's try to find some patterns in the pyramid. Okay, so let's try to find some patterns in the pyramid and see what pattern seems to be easy to implement for us. Okay, so let's say this is the first value and these are the second two values, and then, or let me just draw it. Let me not draw the squares, I'll just write the numbers. Okay, so 1 square, 2 square, 3 square, then 4 square, 5 square, 6 square, 7 square, 8 square, 9 square, 10 square, 11 square, 12 square, 13 square, 14 square, 15 square, and so on, right? So let's say we chose a particular element to drop. Let's say we hit 13 square, right? So then which elements would fall? The ones which are directly above it, right? Now this will cause like a chain reaction. So the ones directly above this will also fall. So this element, this element, this element, and then the ones directly above this. So this and this, and directly above this, right? So these are the elements which will end up falling. Let us take a case in the corner. So if we make this fall, the one directly above is going to fall, so this one, the one directly above is going to fall, this one, and this one. Okay, what about if we hit, let's say, this corner? Then again directly above would be something like this, right? Okay, what if we ended up hitting, let's say, this corner like this? So then these two are directly above, these two would fall, then this would cause this to fall, this would cause this to fall, and then this would also fall. So we need the sum of all these elements. Okay, so how do we calculate this? Is there some way to pre-calculate or pre-compute these values? As you can see, the number of rows is 2023. So the total number of possible values which can be there will be 2023 times 2024 divided by 2. Why? Because this row has one value, this row has two values, this row has three values, and so on. So if you want to know the total number of values in the triangle or in the pyramid, then we'll get something like this, right? Which is 2023. So this is n times n plus 1 by 2 formula, right? And we would get this value. And how much is this value? We can use Desmos to approximate. It is roughly 10 power 6 or 10 power 5 ish, 10 power 6 ish, right? Right. So this is roughly 10 power 6, 2 times 10 power 6. Okay, around. So how, this is not many values. So for each value, if we can somehow pre-compute the answer, then we would simply need to print the answer in big O of 1 for each test case. How can we do that? So now we need to start making observations. And one observation which will greatly simplify the problem is, let's say we have 13 square, right? So 13 square, if we topple 13 square, that means that this diagonal over here gets toppled, correct? This diagonal gets toppled. Let's say this diagonal gets toppled, okay, because they're all directly above. Similarly, if you start at 9 square, this diagonal gets toppled, and then this diagonal gets toppled. So toppling at 13 square or hitting the can at 13 square topples the diagonal of 13 square, and then also topples the diagonal of 9 square, and also topples the diagonal of 6 square. So basically you're adding this diagonal plus this diagonal plus this diagonal, right? So one way we could do this is, if we had the sum of values of these diagonals, then we could use this to calculate our answer by simply doing like 13 square is diagonal plus 9 square is diagonal plus 6 square is diagonal. Okay, so let us do the sub problem. Sum of values of each diagonal. Okay, sum of values of each diagonal. And how can we calculate this? Okay, so again, let me just draw the triangle. Let's say we have 1 square, 2 square, 3 square, 4 square, 5 square, 6 square, 7 square, 8 square, 9 square, 10 square. Okay, so let's say I want to calculate the sum of values of the diagonal of 9 square, which means 9 square plus 5 square plus 2 square. Okay, 9 square plus 5 square plus 2 square. I want this value. Now this value is simply equal to diagonal of 9 square is simply equal to the diagonal of 5 square plus 9 square. Why is that? Because the diagonal of 5 square itself is 5 square plus 2 square. So we're just adding 9 square to that, right? So basically each diagonal of some value, let's say from the row R and column C is simply equal to diagonal of row R minus 1 and column C minus 1, right? So if you have this value as RC, or let's say this is diagonal of 1, 2, 3, 4, so this is 4 comma 3, then it will be from 3 comma 2, right? So, and the diagonal of this will be added, and then also the current value squared, right? The current value squared. So we can say that is I square or something like that, right? So there are many ways we can store this pyramid in our array. We can either store it as a 2D array or a single array, depending on how you implement it. But we get this recursive formula to calculate the value of diagonal. And in fact, this is a DP formula, right? If you know DP, then you can observe that this is a DP formula. And what we can write is the DP of this diagonal I, or the DP of the diagonal at position RC will be the dp of r minus 1 c minus 1 plus this I square, right? I square is simply the ith index or the index value at this position. Okay, right? So this is how we calculate the value of sum of diagonals. Fine. Now what is our objective? Let's come back, we solve this subproblem. So now what is our objective again? Our objective was let me just draw quickly the pyramid again, fresh pyramid. Square, 10 square, 11 square, 12 square, 14 square, 14 square, 15 square. Okay, so when we topple something, for example like 13, then the diagonal of 13 is being added, right? So the diagonal of 13 is being added plus this diagonal of 9 plus this diagonal of 9 plus this diagonal of 6, right? Plus this diagonal of 6. So not just one diagonal, but all these subsequent diagonals in this direction, right? So all these values in this direction, their diagonals are being added together, and that is contributing to our final sum, right? That is contributing to the final sum which we need to print. So how do we calculate this? Again, simply we can say that we can have that this answer, so let's call this answer of 13 is simply equal to diagonal of 13, right? The diagonal of 13. So right now I'm using the index to refer to this, plus the diagonal of 9, right? Plus the diagonal of 9, right? Sorry, not the diagonal of 9, plus the answer of 9. The answer of 9. Why am I saying answer of 9? Because at this particular position, if we want to find the answer will simply be diagonal of 9 plus diagonal of 6. Now at 13, the answer is going to be diagonal of 13 plus diagonal of 9 plus diagonal of 6. Basically, the answer is just increasing by diagonal of 13, right? So that's why answer of 13 will be equal to diagonal of 13 plus answer of 9. Or you can write this in dp terms. So in dp terms, is also dp in a way. So in dp terms, we can write it as dp of 13 will be equal to diagonal at 13 plus dp of 9, right? And 9 is basically, if we do one row back, and same column, so basically like this is row 5 3, right? This is 5 3, then this will be 4 3, right? So that's all we're doing, from 5 3 to 4 3, whatever the answer was, and we're adding diagonal of 13 to that, right? So basically we have figured out our answer. We have figured out that our answer is simply sum of diagonals, and diagonal sums can be calculated with dp. Diagonal sums can be calculated with dp. Also our final answer is simply equal to our current diagonal plus the answer at one level back, right? Answer at one level back, which means going in the opposite direction of the diagonal. So one level back. So basically answer at 13 is equal to its diagonal plus the answer at 9, and so on. So now implementation for this can be a bit tricky, right? Implementation can be a bit tricky. So we'll have a quick look at the code. Yeah, so as I was saying, the implementation can be a bit tricky. That's the main issue we have to deal with for this problem, and otherwise the time complexity will be about big O of n plus t, because since we are summing the values for each diagonal as well as summing the value for each answer, so it's simply going to be big O of n to calculate the pre-processing, right? Pre-processing. And for each test case, we simply need to print the value which we pre-computed. So that's also big O of 1 per test case, right? And the space complexity will be big O of n to store all the answers. So let's have a look at the code to get an idea of the implementation for this. Okay, so have a look at this. So here I'm defining RC as my row count. As you can see, it's 2023 because that's what the question is given. And nmax I'm taking as RC times RC plus 1 by 2, as we discussed. Okay, so now dp1 and dp2 are going to be two vectors which are going to store our pre-computed values. dp1 will be the sum of diagonal at a particular point. Okay, so what does that mean? That means that, as we discussed earlier, so if when you start at 8 and you go up, you reach 4, right? So 8 square plus 4 square will be stored at dp of 8. Similarly, dp of 9 is going to store 9 plus 5 plus 2 and so on, right? That's what I mean by sum of diagonal at each point. What will dp of 2 store? dp of 2 will store the answer at each point. So this is going to be the answer which we are going to return. So basically it will be something like, for 13 square it will be this diagonal plus the answer at 9 square, right? So that's what we discussed. Okay, so that's what dp1 and dp2 will store. We are using a single flat array because I find that simpler to store, right? I find that simpler to store. You can use a 2D array as well, but this is easier for me. So that's why I implemented it like this. And yeah, it does make the logic kind of easier as well. So now we have idx is 1. So this is the current index in 0 indexing. So basically the index of this position will be 0. Okay, the index of this position will be 0. And the index of this position will be 1, right? And then the index of this position will be 2 and so on, right? So that's what it's being 0 indexed for convenience. Also the rows are also being 0 indexed. So this row will be row 0, and then this row is row 1, and then this row is row 2, and so on and so forth. Okay, so this is going to be tracking the current index in our dp. And now we're going to loop through each row. So from row 1, like this is row 0, so from row 1, then row 2, row 3, row 4, so on. We're going to loop like that. We're going to calculate the index of the previous row, the starting index of the previous row, and this is simply because, like, when we are summing our previous answer, or when we're summing the diagonal, we need to know the value at the previous row as well, right? So because we are not using 2D array, we're using single array. To do this, we can simply take the starting value of our row and minus the row count. So then we will reach the starting value of the previous row. So that's why I'm just noting it down as this is the starting value of the previous row. Now we can loop through each value of our row, like from I equals 0. So I equals 0, I equals 1, so on, for each value of our current row. What we are going to do, first we're going to calculate the diagonal value, right? So for the diagonal, what do we do for the diagonal? So for the diagonal, we do, we need to sum the current value. So this is index 8. So we'll sum 9 square plus the diagonal at 5, right? Plus the diagonal at 5 plus the diagonal at index 4, basically. So that's what we're going to do. We're going to do our current index plus 1 squared plus dp of previous row plus I minus 1, right? So previous row is this point and plus I minus 1. So this is plus I. So 1 less than that plus I minus 1, right? And if that does not exist, if I, this only exists if I is greater than 0, right? So for example, here we cannot have an I minus 1. There's no previous I minus 1. There's only I minus 1 at these points, right? In the previous row. So that's why we're making sure that I is greater than 0. Similarly, to calculate the final answer. So the final answer is simply our current diagonal value, So that's dp1 of idx, right? That's dp1 of idx. That's dp1 of idx plus, yeah, so that's dp1 of idx plus the value of dp2 of the parent element, right? Parent element is this one, right? In this direction. So that's why we're making sure that previous row plus I is dp2 is being added, and that's if I is less than row count, because if I is equal to row count, there won't be any parent element this in this direction, right? So that's all, we're adding the previous dp2 value and we're increasing the index. So once this ends, all the values from 0 to n, or all the values of the row count, each value will be pre-computed for the sum of diagonal as well as the answer. So then finally all we need to do is simply print the answer. So input n minus minus, and just print the answer of dp2n, right? dp2 of n stores the value of our final answer. The overall time complexity is n max plus t, right? N max is this value, n max plus t, and the overall memory complexity is n max because that's what we're storing in our dp array. That's all for this problem. If you had any issue with the problem, like you still couldn't get it or you couldn't solve it yourself, and you want to know where to solve such problems, then you should definitely check out and learn dp, as well as, you know, implementation for these like pattern matching type of questions where the pattern is given right in front of you. You just need to break it down and figure out how to quickly and cleverly sum the answer. All right, that's about it for this question. Thanks for watching and see you in the next solution.